This is the second of 3 videos covering the special theory of relativity. In the first video, we considered a situation where there was a stationary observer and a moving observer. We wanted to compare the position seen by the stationary observer and the time seen by the stationary observer with those seen by the moving observer. We found that one must go ahead and relate them in the following way. This was forced by the requirements based on experiments. What I want to do in this video is to see the consequences of that relationship. This is a plot of the position and time seen by the stationary observer. Each point here represents a particular position and a particular time. This point here would represent that x value and that time value. The t-axis is distinguished by x equals 0. In other words, everything happening along here happens at x equals 0. Likewise, anything that happens along here happens at position x. Correspondingly, the x-axis is represented by t equals 0. Everything that happens along here happens at time t equals 0. Anything that happens along here happens at time t. We can do the same for the moving observer. If we go back, we see that the t prime axis must be the axis for which x prime is in fact 0. In other words, x is equal to ut. This is x prime equals 0. Similarly, the x-axis would be given by t prime equals 0. That would mean t is equal to u over c squared times x. Let's put those in on our graph above. The t prime axis was given by x is equal to ut, and the x prime axis was given by t equals u over c squared times x. Drawing that in, the t prime axis would look like this. And the x prime axis would look like this. This is t prime equals 0. The t prime axis is not terribly surprising. In other words, the point which the moving observer would call x prime equals 0 would be where he is located. And that would move along as time progresses for the stationary observer. This axis, however, the x prime axis, is relatively unexpected. You see, what it says is that everything along this line occurs at the time t prime equals 0. That's at odds with what the stationary observer would claim. He would say this, he would see these points as happening later than this point here. In other words, they would not agree about when two things happened at the same time. That's fundamental to understanding a lot of the issues of special relativity. Suppose I wish to measure the length of this rod. I put it up here. I locate this end. I locate that end. And now I simply take a ruler and measure it. Suppose, on the other hand, that the rod is moving, going past me. Now I've got to locate both ends. So I locate both ends. And then I measure it. You might say, you didn't mark both ends at the same time. And that's exactly the issue of special relativity. Two observers will not agree about when 2 points, separate points, are marked at exactly the same time. As a result of this, using the formulas we found earlier, you can find the relationship between the length measured by an observer who sees the rod at rest, 0, and the length measured by a person who sees the rod moving. And in fact, the relationship is this, where u is the speed of the rod. In other words, because of this disagreement about when two things occurred at the same time, in this case, when the marking of both ends occurred at the same time, the person who sees the rod as moving will see it as being shortened. But all of this can be traced back to the fact that they do not agree about when two things were done at exactly the same time. In the first video, we considered this situation where there was a stationary observer and a moving observer. Both were looking at a ball. By very reasonable assumptions, we came to the conclusion that the velocity seen by this observer for the ball should be the velocity that this observer sees the ball as moving, plus the velocity u of this observer relative to that. In other words, the velocity seen by this observer should be the velocity seen by this observer, plus the velocity of the car relative to the stationary observer. Reasonable result, but we did point out that experimentally this is simply wrong. The correct relationship between what this observer sees and this observer is given by this. X prime is the position seen by this moving observer. T prime is the time seen by the moving observer. Correspondingly, X is the position seen by the stationary observer, and T is the time seen by this observer. The two are related through this relationship. So what I want to do now is show you what the correct relationship is between the velocity seen by this observer and that seen by this. In other words, this is simply wrong. And the way you find that is you point out that while x is the velocity seen by this observer times the time used by this observer, x prime is the position seen by this observer, and that's equal to v prime, the velocity seen by this observer, times their time. One simply puts these two into this, and then after a bit of algebra, which I'm not going to carry out, you will find that v should be v prime plus u divided by 1 plus v prime u over c squared. There's a few things to notice about this. If v prime, the velocity seen by this observer, and this person's velocity itself are much less than the speed of light, in other words, v prime and u are much less than c, then this part down here becomes very, very small compared with 1. And we find that v is approximately v prime plus u. Exactly the result we found earlier. Now, on the other hand, suppose v prime, the speed seen by this observer, happens to exactly equal c, the speed of light. Well, we can put that in. Then v would be c plus u divided by 1 plus, here again we would put in c, u over c squared, in which case I end up with c plus u over 1 plus u over c. One of these c's drops out. Now if I multiply top and bottom, I factor out a c from the top, I would get c is equal to, I get c times 1 plus u over c divided by 1 plus u over c. But that's just c. In other words, if this observer sees something moving at the speed of light, The other observer, the stationary observer, will see the object moving at the same speed. Suppose this observer is moving very fast, and they're looking at something going very fast, but less than the speed of light. In other words, suppose u is equal to 0.9 times the speed of light, and v prime is equal to 0.9 times the speed of light. In other words, this person sees this car is traveling at 90% the speed of light. In turn, the person on the car is looking at something also moving at 90% of the speed of light relative to them. Surely I would expect this person to see this object moving at greater than the speed of light. But let's see what this tells us. If I put these two in, I would have 0.9c for v prime plus 0.9c for u. Here I would have 1 plus 0.9c times 0.9c divided by c squared. But this is going to be 1.8c upstairs. The c squareds drop out, and I have 0.9 times 0.9, which is 0.81, divided by 0.81. And the thing to notice is that this number, although very close to the speed of light, is slightly less, right? It's 1.8 divided by 1.81 times c. So in this situation, the speed of this object seen by the stationary observer is still, although close to, is still less than the speed of light. Next time we'll go ahead and follow this even further.